Hello, and welcome to this presentation related to first order differential equations. This is the first presentation in the lecture series, and here we're going to solve equations of the form dy by dx is equal to a function of x. So here's a presentation overview. We commence with underpinning knowledge, which relates to various mathematical techniques required. Next we have a brief introduction, relates to the formation of differential equations and the notation used. Then we consider solving differential equations, considering the general and particular solutions. Then we consider the various types of differential equation within this presentation, all of which can be solved using integration. We also include some extracts from our standard tables. Then we have example 1. We're asked to solve dy by dx is equal to x squared. The example is fully worked through. Then we have exercise 1. This consists of 4 parts. The first part, shown here, and the second part, shown here, require general solutions to be determined. And part 3, shown here, has an initial condition stated, as does part 4, shown here. So we need to find the particular solutions. Then questions 1 to 9 are outlined, and the solutions required are essentially based on those of exercise 1. And here are the approximate start times related to the various sections shown on this slide, should you want to directly review any of these sections, but please note all times are rounded to the nearest minute. Presentation overview continued. The latter part of the presentation primarily related to a kinematics context, where we consider acceleration, velocity and distance. For your reference, we've reviewed these relationships in a previous presentation. Here are questions 10, 11 and 12 related to the kinematics context. They're essentially descriptive questions, but the overall solution sequence is the same as those we have reviewed previously. And here are the approximate start times to the solutions to questions 10 through to 12, but again please note these times are rounded to the nearest minute. And here's questions 13 and 14, again associated with a kinematics context. And here are the approximate start times related to the solutions for questions 13 and 14. Some technician engineering students find these questions particularly difficult because they do require some underpinning knowledge when solving differential equations of the form dy by dx is equal to a function of x. Underpinning knowledge includes transposition of equations and solving simple equations, requires techniques such as expansion of brackets, factorization, etc. We need to be conversant with integration using standard forms, referring to our standard tables. We need to be aware of trigonometric functions, the sine, cosine and the tangent function, and also within some later presentations the reciprocal functions of cosecant, secant and cotangent. We need to be aware of the exponential, e to the x function, and again in later presentations use of the laws of logarithms and the laws and the rules of indices. So you can see why some students do find these questions particularly difficult, because of this array of underpinning knowledge required. Let's consider the formation of differential equations. Differential equations usually arise in theoretical physics and engineering through application of fundamental laws related to a particular problem. Typical engineering problems that can generate such differential equations include Fourier equations for heat transfer, Newton's laws of cooling, charge and discharge of a capacitor, circuit current in an inductor, stress and deflection of beams, and problems associated with metrology, the science of measurement. Let's consider notation and order of differential equations. A differential equation is one containing differential coefficients, for example dy by dx. Examples include the following. Item 1 here, dy by dx is equal to 3x. Item 2 here, d2y by dx squared plus dy by dx plus 2 is equal to 0, which for convenience can also be written in the short form as for item 1, y dash is equal to 3x. For item 2, y double dash plus y dash plus 2 is equal to 0. This relates to the historical background of Leibniz and Newton's almost simultaneous publication of their work on calculus. We can also write these equations in what is termed the d operator form, where capital D means d by dx. So again, item 1 we can write as capital dy is equal to 3x, or item 2 we can write as capital D squared y plus capital dy plus 2 is equal to 0. Here the capital dy is equal to dy by dx, and the capital D squared y is equal to d2y by dx squared. So just be aware of the various formats that can be used within this topic of study. Let's just briefly consider the degree of a differential equation. The degree of a differential equation is that of the highest power of the highest differential in the equation after simplification. So in part A, shown here, we have the equation dy by dx to the power of 3 is equal to 9x, and we have part B here, d2y by dx squared raised to the power of 4 plus 3 multiplied by dy by dx to the power of 5 plus 2 equals 0. So with regards to equation A above, this is termed a first order differential equation of degree 3, and with regards to equation B above, this is termed a second order differential equation of degree 4. And that's purely for background information, as we'll not be considering equations of the form shown above within this presentation. Solving differential equations. Differential equations are solved using the process of integration. Thus, beginning with the differential equation, it is possible using integration, and given sufficient information, to determine the original function. So for example, we'll have dy by dx is equal to a certain expression. We'll be able to integrate this to find y is equal to the original function. Let's consider general, sometimes referred to as primitive solutions to differential equations. If a solution to a differential equation contains one or more arbitrary constants of integration, then this is termed a general solution. The following equation related to beam deflection is a general solution to a differential equation, as it contains two unknown constants, labelled as C1 and C2. So here's an example of an equation. We've integrated twice to get this expression. And notice we have the C1x and the C2 on the right hand side. And because we've integrated twice, we have two constants of integration. Purely for your reference, this equation relates to this beam configuration shown here. Let's consider particular solutions to differential equations. When additional information is stated, enabling the constants of integration to be evaluated, the solution is then termed a particular solution. Thus, if the initial conditions for a beam are known, sometimes also called the boundary conditions, that for example the left-hand end, when x is equal to 0, shown here on our diagram, and the right-hand end, when x is equal to 5 meters, shown here on our diagram, that there is no deflection, then the constants of integration can be found. So here's a repeat of the equation from the previous slide, but notice this time we have constant C1 calculated, but constant C2 in this case calculated to be 0. So that equation relates to a particular solution. So in this context, we can now use the equation by stating any value of x on the right hand side, and we'll ultimately be able to find the deflection y. Purely for reference, here's an extract from a separate presentation related to Macaulay's method. We use this to determine beam slope and deflection values along lengths of the beam, and these calculations relate to the beam configuration on the previous slide. Very briefly overviewing the calculations. So we commence with a second order differential equation, effectively a d2y by dx squared equation. We integrate it the first time, to find a first order differential equation, a dy by dx equation, which is the ones we're considering in this presentation. Notice we have c1 as a constant integration from integrating the first time, and integrating the second time we have the equation for y, but now notice we have two constants of integration, c2 has been added. If we know our initial conditions or boundary conditions in this case, that when x is equal to 0, y is equal to 0, that's the left hand end of the beam, and when x is equal to 5 meters, y is equal to 0, that's this location on the beam. We can find our constant of integration, in this case c2 is 0, and here we've calculated the value of constant c1, it does have a specific value in this case, and that's allowed us to find a particular solution. So within this problem we can now find the deflection at the midspan, x is equal to 2.5 in this case, and we're here by inserting the value of x into this particular equation. Here's our value of y calculated. So that example is actually more complicated than what we're going to consider, as it actually started with a second order differential equation. But hopefully it illustrates how we use differential equations, we integrate them, we solve for constants to find particular solutions. Types of differential equation. First order differential equations can appear in the following three forms. dy by dx is equal to a function of x, dy by dx is equal to a function of y, and dy by dx is equal to a function of x function of y. All of these forms can be solved by the process of integration, and within each case it is possible to separate the y terms onto one side of the equation and the x terms onto the other. Solving these types of differential equations using direct integration is termed separating the variables, variables separable. But in this presentation we're only going to consider equations of the form dy by dx is equal to a function of x. Later presentations will consider differential equations related to the other two forms. For your reference, here's a table of standard integrals we'll be referring to. This slide just contains extracts of the table. There's a more extensive table shown in the notes, but these are the typical integrands we'll be considering within this and further presentations. The integral is shown on the right hand side here. And further reference information, in later presentations we'll be referring extensively to the laws of logarithms, the laws and the rules of indices, and to various trigonometric ratios. Let's consider a solution of differential equations of the form dy by dx is equal to a function of x. So an equation of this form, dy by dx equals a function of x, can be solved directly by integration, with the solution being of the form y is equal to the integral of a function of x with respect to x. Example 1, we're asked to integrate to solve the following equation to find the general solution. Here's the equation, dy by dx is equal to x squared. If coordinate x is equal to 2, y is equal to 3, defines a point on the curve, we're asked to determine the constant of integration and thus state the particular solution. So given dy by dx is equal to x squared, with all these equations we'll be able to rearrange to have the x terms on one side and the y terms on the other side of the equation, doesn't matter which side they're on. So in this case I've multiplied both sides by dx, so on the right hand side I have x squared dx, and I have dy on the left hand side. I'm now going to integrate, so on the left hand side I integrate 1 dy, on the right hand side I integrate x squared dx. These are both of standard forms as shown in the table. They're both of the form ax to the n, so the integral becomes ax to the n plus 1 over n plus 1 plus the constant of integration c. It's assumed here you're familiar with the use of standard integral tables. So on the left hand side integrated 1 with respect to y becomes y. On the right hand side integrating x squared with respect to x becomes x cubed upon 3, and the add our constant integration, I put it onto the right hand side here. It doesn't actually matter which side you add the constant integration as long as you add the c. So this is now termed the general solution. And purely for reference, I've shown a detailed illustration of how we're integrating 1 with respect to y and how we end up with y on the left hand side. I've essentially inserted the y to the 0 here to make it standard form of ax to the n. This is effectively a y to the n integrated with respect to y. Remember that y to the 0 of course is 1, so I've not affected the question, but applying the above solution we can see how we end up with y as the answer. So this term here is effectively ax to the n in our tables. Example 1, solution continued. Now we're going to impose what's termed a boundary condition here. Often it's called an initial condition. I've used the term boundary condition here. And we're given in the question x is equal to 2, y is equal to 3, stated here. So essentially we're now going to generate a simple equation and solve for constant c. So inserting the value for y here on the left hand side, x here on the right hand side. Basically just evaluating, rearranging the equation to solve for c. So next line 2 cubed is 8. I've then subtracted 8 upon 3 from both sides of the equation. Turn the equation round to have c on the left hand side, and c evaluates to 1/3. So now we have our particular solution, y is equal to x cubed upon 3 plus 1/3. On the last line, because the third is common to both terms, I simply factorise, so y is equal to 1/3 multiplied by in the bracket x cubed plus 1. Note that the constant of integration c actually relates to the intercept of the equation with the vertical axis, so 1/3 shown here. So for reference, when an initial condition or a boundary condition is stated in the question, it relates to a point on the curve, plotted here in this case, which is the y equation we derive after our integration process. So exercise 1, parts 1 and 2, we're asked to find the general solutions to the following differential equations. So 1 is dy by dx is equal to 5x squared plus cos of 3x, and part 2, x multiplied by dy by dx is equal to 3 minus 2x squared. Answer shown in the square bracket. I would encourage you to stop the presentation and attempt exercise 1, parts 1 and 2, but the full work solutions are shown on the following slides. So exercise 1, part 1, I'm given dy by dx is equal to 5x squared plus cos of 3x. So here's exercise 1, part 1 solution. So as with all the problems in this presentation, we'll be able to rearrange the equations to have x terms on one side and y on the other. So in this case, all I have to do is multiply both sides by dx. So I will have dy on the left hand side is equal to 5x squared plus cos 3x multiplied by dx. Notice I need the bracket here to ensure my BODMAS is correct. These expressions are in standard form, so we can integrate using our standard tables. To integrate in the left hand side with respect to y, we have y. Integrating 5x squared with respect to x, we have 5x cubed divided by 3. Integrating cos 3x with respect to x, that becomes plus sine 3x divided by 3. And I've added my constant of integration on the right hand side here. For reference, we have used the ax to the n integrand, integrates to this solution, and we've also integrated using the cos ax integrand, integrates to 1 upon a multiplied by sine ax. And note for reference that can also be written as sine ax divided by a plus c. So that's a general solution, and in this case the final solution to the problem. Exercise 1, part 2 solution. We're given x multiplied by dy by dx is equal to 3 minus 2x squared. So again, we can rearrange the equation to have all the y terms on one side, all the x terms on the other. So on the next line, I've divided throughout by x to leave myself with dy by dx is equal to, on the right hand side, 3 divided by x minus 2x squared divided by x. That can be simplified, of course. On the next line, I've multiplied throughout by dx, so now dy is equal to 3x to the negative 1 minus 2x, notice contained in the bracket, multiplied by dx. So just simplify the terms inside the bracket. Just notice the cancelling of the x terms occurring here. Again, both the left and right hand expressions are in standard form, so we can directly integrate. On the left hand side we have the integral of 1 dy. On the right hand side we have the integral of 3x and negative 1 minus 2x with respect to x. Our standard integrands are shown at the top of the slide here. On both sides we will apply the ax to the n solution, but note on the right hand side here the 3x and negative 1, here the integrand is 1 upon x, or x and negative 1, and we inform the solution here is ln x plus c. So on the next line, integrating 1 with respect to y is y, integrating 3x and negative 1, that becomes 3 ln x, and integrating the minus 2x with respect to x, that becomes minus 2x of 2 divided by 2, plus the constant integration again on the right hand side here. So final solution for y is equal to 3 ln x minus x squared plus c. Notice the 2 in the numerator here cancels with the 2 in the denominator here, to leave us with the 1x squared. Exercise 1 continued. Now we've got to find the particular solutions for the given differential equations and the specified initial conditions. So for part 3, we're given 3 multiplied by dy by dx plus x is equal to 6, and we're given that y is equal to 5.5 when x is equal to 3. I would encourage you to stop the presentation and attempt exercise 1 part 3, where the full work solution is shown on the following slides. So exercise 1 part 3 solution. So here's the original equation written on one line for convenience. I'm going to rearrange the equation. First of all, I will subtract x from both sides, so that's what's shown here. Next I will divide throughout by 3, shown here. Notice again use of the bracket in the numerator, 6 minus x is in the bracket. And then I multiply throughout by dx. So now I have dy is equal to, in the bracket, 2 minus x divided by 3. I'm just dividing both terms in the bracket by 3 here, multiplied by dx. Again, the expressions on both sides are in standard form, so we can directly integrate. So integrating 1 with respect to y, y. Integrating 2 with respect to x becomes 2x. Integrating the minus x divided by 3 with respect to x becomes minus x squared divided by 6. And I've added my constant integration on the right hand side here. So again, both sides of the equation are of the form ax to the n, so we integrate ax to the n to ax to the n plus 1 over n plus 1 plus c, as shown here. Exercise 1, part 3 solution continued. Just repeated this line from the previous slide. As part 3 wants us to find the particular solution, we need to impose the initial conditions given in the question. So when x is equal to 3, y is equal to 5.5, 5.5. So on the left hand side I've imposed y, and wherever there's an x on the right hand side I impose the 3. The rest of it's just evaluation, so I'll let you review these calculations at your own pace. And essentially c evaluates to be 1. So now, having found the constant integration, we can state the particular solution for this problem. It's y is equal to 2x minus x squared divided by 6 plus 1. So that concludes the solution for exercise 1 part 3. Exercise 1 continued. This is part 4. Again, we're asked to find the particular solution given specified initial conditions. So this time we have the equation 2 multiplied by dr d theta plus sine 2 theta is equal to 0, and we're given r is equal to 2 when theta is equal to pi upon 2. Note here, instead of having x and y, we have theta and r, but of course the process is very similar to that of the previous solutions. I would encourage you to stop the presentation and attempt exercise 1 part 4, but the full work solution is shown on the following slides. So here's exercise 1, part 4, commencement of the solution. So this time we need to rearrange the equation to have all the r terms on one side, all the theta terms on the other. So firstly I've rearranged by subtracting the sine 2 theta term from both sides of the equation. Next I divided throughout by 2, and finally I multiplied throughout by d theta. So we have dr is equal to negative sine 2 theta divided by 2 multiplied by d theta. Again, notice use of the brackets around the sine function for clarity. Both sides of the equation are standard form. The left-hand side associated with the r variable is of the ax to the n format, or integral shown here, and the sine ax integrand integrates to negative 1 upon a multiplied by cos ax plus c. And again, notice that can be written as negative cos ax divided by a plus c. Now just be careful here, because the sine function is already negative, so when we integrate it using this standard form, which changes the sign, we will move from a negative sine function to a positive cos function. So noting these expressions are in standard form and integrating. On the left hand side we integrate 1 respect to r, becomes r. On the right hand side we integrate the negative sine to theta divided by 2 with respect to theta, and that becomes positive cos 2 theta divided by 4 plus the constant integration c. So our general solution to exercise 1 part 4 is r is equal to, just slightly reformatted the right hand side, a quarter multiplied by cos 2 theta plus c. I would encourage you to stop the presentation for a moment and just think through these lines here, clearly understanding how the negative sine 2 theta when integrated becomes positive cos 2 theta in this case. And before integration the trig function is divided by 2, and after the integration the trig function is divided by 4. Again, that goes to the fact that we have the a in the denominator when we integrate. So integrating the negative sine 2 theta upon 2, we already have a 2 in the denominator, so when we integrate it we get another 2 in the denominator, and of course that makes a 4. This is all related to integration using standard forms, and there are previous presentations related to this specific topic. Exercise 1, part 4, solution continued. Just repeated this line from the previous slide for convenience. So now we're going to impose the initial conditions given in the question. This time r is equal to 2 and theta is equal to pi upon 2. So on the left hand side we insert the 2 for r, and on the right hand side we insert pi upon 2 for theta. Just note inside the bracket the 2 in the numerator cancel with the 2 in the denominator to leave us with cos of pi on the next line, and cos of pi radians is negative 1. And purely for reference, here is a sketch of the cosine waveform between 0 and 2 pi radians, and we can clearly see for pi radians the ratio is negative 1. Be careful if you're using your calculator to be in radians mode, because the pi upon 2 is an angle in radians, it's equivalent to 90 degrees. So evaluating, we find c is equal to 2 and 1/4, or 2.25 in decimal. Exercise 1 part 4, solution continued. Again, repeated this line from the previous slide. So to find the particular solution, we simply insert the value of c calculated on the previous slide, 2 1/4. On the next line, I've just actually written that as a top-heavy fraction. 2 1/4 is a mixed number, refer back to our fractions presentation, and 9 upon 4 is a top-heavy fraction. And I've just done that because the final solution requires r to equal to a quarter of cos 2 theta plus 9. So I just essentially factorise on the quarter from this line to this line. So that's the full solution related to exercise 1 part 4. For your reference, here are some questions related to differential equations of the form dy by dx is equal to a function of x. Questions 1 through to 5 shown on this slide here. Question 1 is the standard form ax to the n. Question 2 will have the form ax to the n and sine x. Notice in question 4 we have an exponential function that relates to this item within our table. And again, we've reviewed exponential functions in previous presentations, and also integration using the exponential function in previous presentations. Note the integral is 1 upon a multiplied by e to the ax, but that can be written as e to the ax divided by a, as shown here. The final solutions to all questions are shown on the right hand side. Notice these are all general solutions because they all contain a constant of integration in the final solution. And questions continued, question 6 through to question 9. These all result in particular solutions because each question has been given an initial condition. Answers are shown on the right hand side in the square brackets, but they contain no constant integration across. Just note, question 7 uses the variables of theta and r, and question 9 uses the variables of t and theta. You will need to provide your own solutions to these questions, as there are no worked solutions within the presentation. We're now going to consider some contextualized questions that relate to the relationships between distance, velocity and acceleration. You know from previous work that differentiating distance respect to time produces velocity, differentiating velocity respect to time produces acceleration. So therefore integrating acceleration with respect to t will determine velocity, and integrating velocity with respect to t will determine distance as a function of t. So we need to be aware of those relationships when we consider the following questions. There are previous presentations related to the differentiation and the integration of these quantities. This is a very important underpinning relationship within mechanics. So here are the further questions, question 10, question 11 and question 12. The answers are shown in the square brackets on the right hand side here. All-worked solutions will be shown to all these questions. So here's question 10. The acceleration of a body, A, is equal to its rate of change of velocity, dv by dt. We're asked to determine an equation for v in terms of t, given velocity is u when time t is equal to 0. So we're effectively finding the particular solution here. So here's the commencement of the solution. We start the problem from the equation dv by dt is equal to a. That was a hint given in the question. So multiplying both sides by t, dv is equal to a multiplied by dt. Both these expressions are in standard form, so directly integrating. Let's put a standard form shown in the table here. So on the left hand side, integrating 1 with respect to v, integrating on the right hand side a with respect to t. Our general solution becomes v is equal to at plus c. Question 10, solution continued. Just repeated this line on the previous slide for convenience. Now imposing the initial condition given in the question, when t is equal to 0, v is equal to u. So we have u on the left hand side of the equation, place t on the right hand side of the equation, so we can clearly see that c is equal to u. So our particular solution is v is equal to at plus u. Though conventionally in most textbooks that's written as v is equal to u plus at. So that's a full work solution for question 10. Question 11. The velocity of a body, v, is equal to its rate of change of distance, stated as ds dt. We've got to find an equation for distance s in terms of t if v is equal to 5 plus 2t and s is equal to 0 when t is equal to 0. So, from the information given in the question, we commence from ds divided by dt is equal to v. On the next line, we simply multiply both sides by dt, so ds is equal to v dt. But in the question, we're informed that v is equal to 5 plus 2t, so ds can be written as 5 plus 2t in a bracket, multiplied by dt. These expressions are in standard form, so integrating as per the table shown below. So on the left hand side we integrate 1 with respect to s. On the right hand side we integrate 5 plus 2t with respect to t. So left hand side integrates to s, and using our standard form on the right hand side, 5 integrates to 5t. The plus 2t integrates to plus 2t squared divided by 2, plus the constant integration on the right hand side. Note here the 2 in the numerator cancel with the 2 in the denominator. So we end up with distance s is equal to 5t plus t squared plus c. That's our general solution for question 11, but of course we need to now impose the initial condition given. Question 11, solution continued. Just repeated this line from the previous slide for convenience. Now we impose the initial condition given, t is equal to 0, s is equal to 0. So on the left hand side we have 0 for s, and on the right hand side we replace t with the 0. So we can clearly see in this case c is equal to 0. So we can now write down the particular solution. S is equal to 5t plus t squared. That concludes the solution for question 11. Here's question 12. The gradient of a curve is given by dy by dx is equal to 4x minus x cubed divided by 6. We've got to determine the equation of the curve if it passes through the point 2, 3 and 1/3. So here's commencement of the solution. So given dy by dx is equal to 4x minus x cubed divided by 6. On the next line, we simply multiply throughout by dx, so dy is equal to the 4x minus x cubed divided by 6 in a bracket, notice, multiplied by dx. Again, these expressions are in standard form, so we can integrate as per the table shown here. I'll let you review the integration process, all standard integrals here. Essentially, y is equal to 4x squared divided by 2 minus x to the 4 divided by 6 times 4 plus the constant of integration. Question 12, solution continued. So we now have our general solution. So y is equal to 2x squared minus x to the 4 divided by 24 plus c. Just tidied up the right hand side from the previous slide. We now impose the initial condition given. X is equal to 2. Y is equal to 3 1/3. So on the left hand side we have 3 1/3. Right hand side replacing the x with 2. And evaluating c is equal to -4. So we have the particular solution. Y is equal to 2x squared minus x to the 4 divided by 24 minus 4. And questions continued here related to first order differential equations of the form dy by dx is equal to function of x. Question 13. An object is thrown vertically upwards with an initial velocity u of 30 meters per second. The motion of the object follows the differential equation stated here. ds by dt is equal to u minus gt. We're informed that s is equal to the height in meters at time t seconds, and g is 9.81 meters per second squared. We've got to determine the height of the object after 4 seconds if s is equal to 0 when t is equal to 0. Answer shown in the bracket on the right hand side here. And question 14, the angular velocity denoted as omega of a flywheel of moment of inertia I is given by I multiplied by d omega dt plus k is equal to 0. We're informed that k is a constant. We've got to find omega in terms of t, given that omega is omega naught at time t is equal to 0. Answer shown in the bracket here. I will show you the full work solution to these questions on the following slides, but I'm going to let you review the solutions at your own pace. So here's question 13, commencement of the solution. As I said, I'm going to let you review these solutions at your own pace. I've tried to label the solutions, so hopefully you can follow the steps involved here. Standard integration as in the previous questions. Question 13, solution continued. Again, I'll let you review the solution at your own pace. Final answer for S stated here. And question 14, commencement of the solution. Again, I'll let you review this at your own pace. Again, it's standard integration, ax to the n, solution. General solution shown here at the bottom of the slide. And question 14, solution continued. Initial condition imposed and particular solution derived. Particular solution for velocity shown here. Here's the bibliography used to help generate this presentation. A very good maths book for technician engineering students. And I hope this presentation has been of some use to you. And as always, thank you for viewing.